Okay, we're recording. Okay, so last time we talked about change of variables. Oh, forgot to pull the screen down. Talked about change of variables and did several examples. Various sorts. When I went through and explained where the change of variables formula comes from and how to think about it, etc., I never did explain where the stretching factor formula came from. I kind of swept that under the rug. I pointed out, and I think it's borne out, that there was enough going on as it was. Right? So now that we've got that mostly settled, I hope, let's dig down a little bit and talk about where this stretching factor formula comes from. So here's a version of our diagram that we have. Keep in mind the idea is that we have some domain whose image is another domain, starting with an integral on the right side and trying to pull back that integral over to the left. And remember, I talked about how if you have a little bitty piece of area on the left, you can talk about what its image looks like over here on the right. And it's going to be kind of a parallelogram looking thing. And keep in mind what the stretching factor is. The stretching factor is what do you multiply by this yellow area to get that blue area? How much bigger? By what factor is that blue area bigger? Or smaller, right? But by what factor is it changed, right? From where it came from. So what we're going to do is we're just going to take this blue area and we're going to compute it. I'm going to write down a formula for this area. And the very first step in writing down that formula for that area is just to recognize that we have one already from Chapter 1, arguably from Math 218. But if you want to know the area of a parallelogram, the area is the absolute value of the determinant of the matrix you get when you take the first vector here and make that your first column, and then you take the second vector here and make that your second column, right? So that's old news. Now, what these vectors are, we've yet to discuss. We'll get to that in a second. But in general, we got a parallelogram in 2 dimensions, so old formula. Okay, now let's talk about, though, where do these defining vectors come from? And I'm going to start with the first one here. This first defining vector for that parallelogram, well, keep in mind where it came from. This whole thing is the image of this whole thing, right? So this edge of this parallelogram is the image of this edge. Color change. There we go. This edge over here on this side. And these are vectors. You can in fact think of this edge as representing a change in the input to G, and correspondingly its image as being the corresponding output change of G. So as such, right, this matrix, its derivative, the derivative of G, is what relates this dark green input vector to that light green output vector. Now, what is this dark green input vector? The dark green input vector, this is actually a pretty easy one. I mean, it's horizontal. It's exactly in the U direction. It's got a width that's du, right? That's the width of this little rectangle here. And being as it's pointing in the U direction, the direction is the E1 vector. So this is a pretty easy. We know the direction, we know the magnitude, therefore we know the vector. Applying dg to it tells us that vector, and that is our first column. And then likewise for the second column, right? It's very, very analogous. This second column is this because, well, it's dg applied to that vector, E2 dv. It's in the E2 direction. The height there is dv. So thus that, and thus that is that. So it's really just kind of an application of, let's see how to say this. I mean, obviously there's the geometry formula of how to find the area of a parallelogram, and this kind of thing comes in handy surprisingly often. But it's an application of understanding the derivative as a tool for turning input changes into output changes. And now, we're not done yet. What we've got now is at least an algebraic foot in the door. Now keep in mind what I was computing here. I was computing this area. Right, that area, absolute value of the determinant of the matrix. And what are we going to do with this monster? Well, a couple of easy observations. First, this du right there, that's a scalar in the first column, and scalars in columns factor outside of determinants. So that's a nice little quickie. Likewise, the dv there, also a scalar, factors outside of determinants. So the du and the dv factor out. Next, let's think about what's left over. What can we say about this matrix right here? And this is another kind of tricky little observation. I'm going to think about the columns of this matrix. Let's look at this first column. What can I say about this first column, dg applied to E1? Old fact of linear algebra. When you multiply a matrix times a standard basis vector, you get the corresponding column of that matrix. So this, what I have circled in orange here, because I'm multiplying by E1, I'm going to get the first column of dg. Let me say it a little bit differently. The first column of this green matrix is the first column of dg. See what I'm saying? Right? And then analogously, the second column of this green matrix is the second column of dg. So this matrix, this green matrix that we're trying to understand, it has the same first column as dg. It has the same second column as dg. It's dg. So neat little observation. So that's how this simplifies, and we basically win at this point. We have computed this blue area. Notice it has showed up explicitly as a multiple of the yellow area, and so we see our stretching factor. What is it that G has done? By what factor has this change variables function increased the area? Well, there it is. There's your stretching factor, just as we stated previously. So I think that's a nice little argument. It's good practice thinking about derivative matrices and determinant rules, and a lot of linear algebra in there as well, right? But a neat argument. Okay. I'm going to say basically the same thing goes down in 3 dimensions. All right, we started off in 2 dimensions. It's easier to draw the pictures. But if you were to have this scenario where you have some domain in, let's call it UVW space, and if you push it forward by some function to whatever its image looks like in, let's say, XYZ space, and if you want to do an integral right on this, oh my gosh, what a horrifying domain this is, right? Can you imagine trying to slice that thing up? If this is your domain for a triple integral, we are badly in need of an alternative means of computing this, because slicing this up is it's a nightmare, not only because of how many pieces it would have when I sliced it, but also because it'd be so hard to even try to visualize and draw what those pieces are. So basically intractable the way I have it drawn there. So the big idea is that everything over here can be pulled back through the change of variables function. Exact same idea. So this integral turns into this integral. A lot of that is just the plugging in itself. XYZ is G of UVW. That's what G does. That's just plugging in. Right? So that part of the pullback is pretty straightforward. You'll notice again we have this issue of what to do with little pieces of now volume over here, whatever these little volumes are. And presumably they will again be stretched out versions of wherever they came from. Right? Again, then I just need to know what is the factor by which little pieces of volume get stretched out. And it turns out to be the analogous formula. And it looks identical, in fact. Right? It looks like it's exactly the same point. It's the absolute value of the determinant of the derivative matrix. But I say analogous instead of identical because, of course, this is a different kind of derivative matrix. This is now 3 by 3. This is the partials of all of the outputs, x, y, and z, with respect to all of the inputs u, v, and w. So it's a 3 by 3 matrix. But yeah, again, morally, kind of the same result. Okay, now I think a nice exercise, I want to encourage everybody to take a whack at this. Nice exercise is to try to confirm for yourself that this is the correct stretching factor formula. The way you're going to do that is you're going to shamelessly copy, right? Not transcribe, right? But adapt this setup and this argument to where you have a three-dimensional, not a sub-rectangle, but a sub-box. Right? The image will be a three-dimensional, not parallelogram, but parallelepiped. And these vectors are the images of those vectors by the derivative transformation, standard basis vectors, and all that. Right? And the argument goes through analogously. But I do think it's a healthy exercise to draw the pictures, think through every step in the argument, and make sure that you are comfortable. Try to present an actual argument analogous to this that demonstrates that the stretching factor, as claimed, is that. Okay. So again, that's something I encourage you to take a whack at. As usual, if you get stuck on that, not sure where to go, come to my office hours. Happy to help. Other options, of course, porters, office hours, help room, classmates, whatever. Okay. All right. Now I'm going to show you an example of a three-dimensional change of variables, but I do need a side theorem first. This is a neat observation. Another one I want you all to check for yourselves. It's a good exercise. But if you have a linear transformation written as a matrix, amazingly, the derivative is the matrix itself. And that seems a little bit surprising somehow. It kind of feels like it ought to be harder than that or something. But in fact, we've already seen an example of this a few pages back when we were talking about rotations, counterclockwise rotation. Right? We had this counterclockwise rotation here, T, that we wrote as a matrix. Right? And check it out. The matrix that defined the linear transformation, its derivative, same matrix. So I don't know if you noticed that when we were doing this example. I didn't point it out specifically, but like I say, we've seen it before, right? So anyway, this always works, and again, so don't feel the need to do this in in by in generality, but maybe persuade yourself that for all 3 by 3 matrices, right? That when you write down a matrix, A, B, C, D, E, F, G, H, I, whatever, define a linear transformation, take the derivative, you get that same matrix back. Okay. All right, so let's use that fact now. So suppose we've got a parallelepiped, hard to draw, parallelepiped, and let's see here, it's defined by these three, let's see, color choices, these three vectors, and if you got 3 vectors, that defines a parallelepiped, corner at the origin. And suppose that's your domain, right? And, well, again, a fairly ugly scenario, right? Looking at the way this thing is kind of leaning and angled, and it's a lot of corners, right? It looks very, very cornery and edgy. That would be a big problem as a domain for a triple integral. If you had to actually crank out directly, regular XYZ slices, that's a nightmare. Okay. All right. Now, here's a really clever move. Again, I'm showing you because someone showed me. Right? This is one that everyone should keep in mind for possible future use. If you have a parallelepiped, let's see how I can. If you have a parallelepiped defined by certain vectors, as we do, if you take those vectors, make those vectors the columns of a matrix, use that matrix to define a linear transformation. If you set it up like this, then the parallelepiped is actually the image, by way of that linear transformation, it's the image of the unit cube. Really neat fact. Any parallelepiped defined by any three vectors, you can view as being an image of the unit cube by that matrix. So now let me try to persuade you that this is true. I'm just making a huge assertion here. It's a pretty straightforward argument, I think. But let's just literally take this matrix here. I'm going to take these, again, our given vectors, use that to define a matrix, like so. We're going to ask then, what does that matrix do to the standard basis vectors? And, well, if I multiply this matrix times E1, matrix times the standard basis vector gives you a column. And so the image of that first vector is the first column, which is the first defining vector of the parallelogram, as it should be. Right? Does everybody see the sort of what's going to happen there? And so likewise for the second and third. So it's a very convenient little trick. Everything kind of lines up, and boom, I can now view my parallelepiped as an image. Okay. All right. So it's all over with the shouting. If I want to compute an integral here on this very unattractive parallelepiped, right? I'll just do the change of variables. We'll just do the pullback. Notice that the pullback, this is doing exactly what change of variables says. Dx, dy, dz is stretching factor times du, dv, dw. Let's see here. The new domain is the pullback domain, unit cube. Everyone's favorite domain for a triple integral. Zeros and ones, all constants, right? Couldn't ask for anything nicer. Don't forget, of course, to carry over the rest of the integrand. And now we just have to kind of punch out some little details. So in particular, what is this matrix? The matrix that we get, the partials of x, y, and z with respect to u, v, and w, that's the derivative matrix of our linear transformation, and the derivative matrix is that same matrix, right? So this derivative matrix is a freebie. This is a determinant. That determinant is just the determinant of that matrix that's made up of columns that are the initially given vectors. So, but basically no computation, right? The given vectors tell you the matrix, which happens to also be the derivative matrix. So that's all recopied, yeah.
When you do T of U is a times unit vector, what is that x vector that you get?
Oh, yeah, I'm just pointing out that this is just kind of a reminder that being a formula for for this function here, I'm just pointing out the thing that comes out. Colors. The thing that comes out is the output value. That's the point x comma y comma z. That's just x, y, z. That's all it is. Yeah. Right. Okay. So, and then we have a much more desirable integral to compute here. Again, this integral. Now the integrand looks a little weirder, right? But notice this is just a constant. It's some number that you can punch up, and this z. You do have to rewrite what z is, after all, right? Z, of course, is the third output component of the function. The third output component you can see from these coefficients right there. And so that's what Z is. Right here. Everybody good? Bunch of steps, right? Bunch of little details, bunch of stuff that all fits together in this example. But ultimately, this is just applying change of variables for 3 dimensions. And again, we turned a monstrously brutal triple integral rectangular problem into a world's easiest triple integral. Okay. Everybody feeling good? Yeah. Mm-hmm.
Can you explain how you got Z again?
Yeah. So don't forget. I mean, the way this linear transformation is defined is you take the matrix, you multiply by UVW, right, and that gives you XYZ. Right. Let me zoom in there. Yeah. So this matrix times UVW then is going to have 3 output coordinates. The first output, wrong arrow. The x coordinate, the first output is going to be that, right? And then likewise the second, analogously the third. So the third output coordinate, that z, is going to be that, and that red dot product is that. Is that cool?
Yep.
Everybody happy? Okay. All right. So, if this were my book, this is where I would end a section and start a new section, because we've done a lot of stuff and we've got a whole bunch of more stuff that's coming that is connected but also qualitatively different in some important ways. And so I would call this a new section. On the other hand, what we're about to do is related enough that there is a point of view that says, yeah, sure, it makes sense to have this in the same section. But again, the section got monstrously huge, so oh well. We're going to talk about what it means to do an integral in a different coordinate system. This is a very powerful idea. Wanted the highlighter. There we go. A very powerful idea, doing an integral in a coordinate system. And the big point on how I want you all to think about this, what does it mean to do an integral in a coordinate system, is that you're using change of variables. It is literally a change of variables. So, to start moving in that direction, let me point out that a coordinate system is, in fact, a change of variables function. So here's how we've thought about a coordinate system, the polar coordinate system. X and Y are certain formulas involving r's and thetas. You may recall I suggested that it's useful to view that as being a function, and it's useful for more than just this. Right? It's useful for kind of reminding yourself that, don't forget polar coordinates are not unique. Right? Rectangular coordinates are, but polar coordinates are not unique. Because they are really, this function can have weird properties. This function can be not one-to-one, for example. And so the polar coordinates, of course, are not unique. Okay, anyway, what we're going to do with this now, though, is to observe that even though I thought of this previously as a coordinate system, as, r and theta coordinates will allow me to compute x and y coordinates, I'm now going to reconceive of this as a change of variables function. Here's a 2-dimensional space to which I apply a function, and the target is a 2-dimensional space. And we can talk about pulling back through this change of variables function. And that's basically, this is the first step anyway, toward doing an integral in polar coordinates. Okay. Many details to follow. The first detail is to talk about the stretching factor. Here's our Jacobian determinant. This is going to lead to our stretching factor, right? This is something that everybody should compute once in their lives. I've done mine. It's your turn. Give it a shot. It's not that big a deal. You have your formulas right here for x and y in terms of r and theta. You just have to compute certain partials, write them as a matrix, take the determinant. Again, everyone should do that. It's going to take you about 30 seconds. It's not a big deal. And the nice punchline, though, is that you get just r. Very handy. And so by virtue of this being just r, the stretching factor, of course, don't forget, stretching factors have absolute values in them. The stretching factor is the absolute value of r. Yeah? Details, again, to be supplied by y'all in doing that algebra. Okay, I'm going to call this bad news. It's bad news because this stretching factor is going to have to go into our integral eventually. This is going to be part of our new integrand. And it's got absolute values in it. I don't like absolute values. Nobody does. They're weird. They basically say you have to, okay, let's consider this side, and we'll cut it, and we'll consider this side. It's just an annoyance, right? So what we're going to do is, faced with this annoyance that every time we do an integral in polar coordinates, you're telling me I'm going to have to deal with an absolute value every single time? Let's look for an alternative, and the alternative is to make a choice. Very specific choice. We have a good reason for this now. I am going to always choose positive R's. So that, right, for the specific purpose that if I do this, then knowing that R is positive allows me to say, oh, R is positive. I don't need the absolute value anymore. Now I can just say the stretching factor is just R. Nice little compact formula. No absolute values. Much better. Okay, so we don't make this choice because we have to, right? I emphasize there's nothing about these formulas, these polar coordinate conversion formulas, there's nothing about these formulas that says R has to be positive. Right? So heretofore, R has not had to be positive. We are choosing for self-interest at this point, right? To always do things in such a way that R is positive, so that we can have this convenience. Okay. Alrighty. And pretty much the exact same for cylindrical. Oh yeah, question.
So does choosing R as positive just like change your theta balance so that you know?
Well, you have to change your theta. You have to set things up with your theta bounds so that R is in fact always positive given your choices. That's right. So that's right. It does limit you, and that by the way is the reason why I didn't want to do this earlier. When we first introduced polar coordinates, I didn't want to just arbitrarily say R has to be positive because it didn't. There was really no reason to tie our own hands that way at the time, but now we do. Yeah. Okay, good question. Cylindrical, pretty much the same deal. We have these formulas. They define the cylindrical coordinates function, which I can choose now to view as a change of variables function. And I can talk about, well, if I have a three-dimensional solid, I can talk about pulling back through this change of variables function. Being change of variables, I'm going to need to compute that stretching factor. Well, the Jacobian determinant, right? We still have an absolute values issue. But you can compute this out. You can probably hear this one coming. I think everyone should do this once in their lives. I've done mine. Now it's your turn, right? Very easy calculation. Shockingly similar to the polar coordinates. Analogous calculation, right? So you're going to feel like you're doing the exact same thing again. And then again, we find ourselves in this situation where our stretching factor is again an absolute value. Again, we don't like that. Again, we'd like to avoid. What can I do to make those absolute values go away? Well, I'm going to choose, now that I have the motivation to do so, I'm going to choose R to be positive so that the absolute values will go away. And so we have to restrict ourselves then just to positive, never negative, just positive values of R, so that our stretching factor formula will be nice. Okay. All right. Again, pretty analogous with spherical coordinates. Again, formulas, conversion function, reinterpret as a change of variables function. Compute the Jacobian determinant. Again, your turn. Right? Everybody should do this. This one's going to take you a few more minutes. The algebra gets a little weirder. There's a lot of cosines and sines. And the good news, and again, I want everyone to do this, but I'm going to point out what makes this nowhere near as bad as it looks, is that as you start going through this and taking this determinant, the Pythagorean identity comes up several times and turns lots of ugly into one. There's lots of, cosine squared plus sine squared, 1, in this calculation. When you go through the whole thing, here's the answer you should get, I'll say, rho squared sine phi. And again, then, we find ourselves in this situation where the actual stretching factor, right, is the absolute value of this thing. And we don't like absolute values. And how can we avoid these absolute values? What do I have to do, right? What have I got to do to make sure that this thing on the inside is positive so that I can throw away the absolute values? Right? And one thing you're going to notice as the analogy starts to break down, you kind of think by analogy that, we had to require R to be positive up there, so I'm probably rho. Maybe we require rho to be positive. Think about it from what would happen if I knew that rho was positive. Not much. That was getting squared. That factor was going to be positive anyway. It's got nothing to do with rho. Okay. What you need to worry about is the sine phi. Right? The sine phi is the issue. That's the thing that I need to figure out. What do I got to do to make sure that thing is positive? And a little bit of trig will point out that if you make this choice, you always choose phi to be between 0 and pi. Then you'll be good. Sine phi will never be negative. So, kind of a weird thing then, right? But always choose phi to be between 0 and pi. Here's the good news. Phi equals 0 is like this. Phi equals pi is like this. These are the values of phi that you probably wanted to use anyway. Right? So, this is a win-win. Always take the easiest route, and then you will end up with the easiest possible scenario for your stretching factor. Okay. Alrighty. So let's do one. Here is an integral that I want to compute. I want to compute this integral here, defined on the unit disk. First quadrant portion of the unit disk. Whoops. So there's our domain R. And it's not the worst one in the world. You could slice this up. It's not really a problem. You are going to have, though, this curve involved, and this curve, being as it is a circle, if you solve for x as a function of y or y as a function of whichever way you do it, the square roots. So you got square roots in your inner bounds, which means you've got square roots in your outer integrand, and that means this could turn ugly, even though it doesn't look that bad, right? Okay. All right. I claim that this first quadrant portion of the unit disk is the image of a rectangle by way of the polar coordinates function. Now let's kind of talk through that. I claim that this is the pre-image back here. Let's think about the edges that define our actual domain. This edge here, what can I say about r and theta on this edge? Well, on this edge, theta is 0 for this whole edge, and r goes from 0 to 1. Okay, so, that's, boom, right there. That's this edge. Let's think about this edge there. This edge has r fixed at 1, and theta goes from 0 to pi over 2. Well, boom. Yeah, everybody with me? What can I say about this edge? Well, let's see. Theta is pi over 2. R goes from kind of 0 to 1. Okay, so there you go. And then I'm going to point out as a quick observation that this edge over here is r equals 0. So that's really all just that point right there where r equals 0. And sure enough, everything on the inside there then has to go to all of that there. Everybody happy? So we've got ourselves a pullback domain, and we're in business, right? So I can pull back. Let's see here. That is just r squared. Dx dy is stretching factor times dr d theta. Don't forget your stretching factor. That r right there was our stretching factor from the previous page. And we've got ourselves our new domain. Our new domain, of course, is, we've already agreed, this, conveniently, it's a rectangle, which means that r and theta range over those values, and we're in business. We've got a nice, easy little integral here. And sure, the variables are r's and thetas instead of x's and y's, but this is a very doable little integral. Just to be clear, your integrand is all of that. Don't forget to include the stretching factor is, of course, part of your integrand. That's why it's there, right? So your integrand here is now r cubed. The r antiderivative of r cubed is 1/4 r to the 4th, right? A lot of people kind of forget to stick the r in there. So heads up on that. And then arithmetic and fundamental theorem and all that. What do you think? Saved ourselves loads of trouble. Again, this would have been at best, inconvenience, and at worst, it could have been a nasty, multiple integrations by part. I don't know. It's square roots are always weird when they're in your bounds. We avoided that completely. This was all polynomials. Nothing to it. Okay. All right. So now the reason I do this example this way, I mean, this is arguably doing an integral in polar coordinates, but it really just looked like I used change of variables. I did use change of variables. And so it just looked like I used polar coordinates as a change of variables function, and why would we talk about the new terminology of doing it in polar coordinates? That comes from this next step, this streamlining of the process. So I've got my pullback domain, whatever it might happen to be over here, right? And I've got to do slices of my pullback domain, and my slice, theta slices, of course, look kind of like this. Those are all theta slices because they're perpendicular to the theta axis. Yeah. Well, that's fine. But these theta slices, I can see them over here in the xy plane. Because, for example, that slice right there, theta equals 0. All right, there it is. Theta equals 0. Slightly higher value of theta? Oh, okay, well, there you go. Each one of these theta slices can be viewed in the xy plane accordingly. And you just have to remember then what these slices look like. It's a question of, again, these curves in r theta, what do they look like in the xy plane? Just remember going forward that when you're taking theta slices, you're really kind of slicing like this, right? You're slicing, you might call it radially outward from the origin. Those are now what I'm going to call theta slices in the xy plane. Likewise for r slices, same deal, same punchline really. Constant values of r, aka r slices. Well, each one of those is a kind of a part of a circle. And better yet, you can see by looking at both of these together, what do r slices of theta slices look like? And I'll remind you, the way we had this written here, right, that's what I'm going to actually need. I'm going to take theta slices of my whatever it is, and then I'm going to need to take r slices of the theta slice. And so let's play that one out. Here's a theta slice. Let me draw that theta slice down here. There's that theta slice. R slices of that theta slice, as you chop up that theta slice, those R slices are like this. Effectively, as you move along the theta slice in the R direction, you're just moving along that theta slice, well, outward from the origin, you might say. Right? So the big idea then, what I did over here, I had my initial domain. I don't like it. I did the pullback. I understood and drew my pullback domain so that I could slice it up, kind of in the usual way, flat R slices and theta slices. I can see exactly what they look like in the R theta plane. But I kind of don't need this anymore. Everything that I saw from this picture, I can see it over here. I can see what my theta slices look like. I can see for a given theta slice, I can see what happens as R moves. Right? Here's R equals 0, and there's R equals 1. You can see it all in this picture. You don't have to draw your pullback. So here's that same example again. Oh yeah, go ahead.
Is it considerably more inconvenient to make the stretching factor?
Sorry, one more time. Say it again, please.
Is it a lot more inconvenient to make the stretching factor go from rectangular coordinates to?
Yeah. There's a lot of awkwardnesses there. Yeah, I wouldn't advise doing that. Yeah, I'd stick to this direction. Yeah, absolutely. Interesting thought. I like the thought. Okay, so here's same question. We already did this. We had a domain. We kind of pulled it back. We saw that there was a new domain over here. But as I've got already drawn in here, we're going to not think about it that way. Yeah, it's there. Yeah, it is a change of variables. Absolutely, of course, right? Just don't look at it. Don't draw it. Everything we were going to do on this side of the picture, let's do it all over here. And notice, I can just, from the shape, I can start doing theta slices. Here's my first theta slice, where theta is 0. And then I do my theta slicing. And then here's my last theta slice. Color choices. Last theta slice is right there, where theta is pi over 2. And yeah, it's the same as I would have gotten over here, but why bother to draw this whole new picture that's it's a certain amount of trouble to figure out what that new picture is? You can see what you need from it right here. Theta goes from 0 to pi over 2. And notice that that's right here in the bounds. Theta, 0 to pi over 2. And then furthermore, for a given theta slice, looking at that theta slice, what we're actually interested in, of course, is just this part. We start there where, okay, yeah, sure, I could think of that as being this point over here, and yeah, I can look and see what its R coordinate is. Sure, I could, but I don't need to, because I can see right here in this picture, it's at the origin. That's where R is equal to 0. And I can see where this ending point is. It's on that curve. R equals 1. And notice R 0 to 1. Exactly what we had before. Yes?
I'm just a bit confused on the choosing R to be positive. If we had like a semicircle or something where some R's are negative, does that affect in any way, or is
I don't know. I'm not sure what you mean when you say R is negative, right? I mean, so R, we can choose R to be various different values depending on how we choose to view a point, right? So this point here, for example, I can choose to view that as, this theta with a positive value of R, or I could also choose to view it as being that theta with a negative value of R. That's a choice, right? So what I'm saying is, let's not do this one, right? Don't view points in such a way that R would have to be negative, because it messes up our stretching factor formula. We get absolute values, and I don't like it, right? It's totally a choice, right? It's not that you can't do this. It's that you're well advised not to. And so just always choose to take the point of view where theta defines a direction such that R is positive. Does that make sense?
Yes, but then if we do have 3/4 of a circle, for instance, would we have to sum of...
Yeah, no problem. If we have 3/4 of a circle, let me see if I can find I didn't really leave myself much space here. I'll tell you what, I'm going to do a new page. 3/4 of a circle. Right? There's our thing. Okay, so I'm going to do this with theta starts there at 0. Theta is going to go all the way around like this let's see, what is it? 3 pi over 2. Right? And notice for all of these thetas, the points that I'm interested in, for every value of theta, we're starting there and we're going outward to there. So all of these r's are positive. Is that cool? Yeah. So what you don't want to do is choose, make some odd theta choices such that, these points over here I could view as being these thetas. Right? It'd be weird, but you could conceive, these directions do get you over here, but it'd be negative r's. And so I'm just saying, just don't do that. This thing that you would never want to do anyway, don't do the thing you don't want to do. Yeah. Okay, good questions. Okay, and then everything else as before. So this is where it starts to really look like we're kind of, you can hardly even see the change of variables, right? I had a domain, I sliced it, r and theta slices instead of x and y slices, but I did this polar slicing of it, and then I just kind of wrote down the integral, and off you go. And the change of variables is there. Again, you are truly doing a change of variables. You just don't see it. So this is what we call doing an integral in polar coordinates. It's a hidden change of variables using the polar coordinates function as a change of variables function. Okay, here's another example. Suppose you have the unit disk, right? This whole thing here. Unit disk. Well, you can think of that as starting there, where theta is 0, and then theta kind of goes all the way around, right? Here's your theta slices, and you just kind of keep going all the way around. And then your last slice is when you get back to where you had been. But of course, you've gone all the way around. Theta's been increasing, and you've done a full turn. So when you get back to when you're done, right? Theta will have increased up to 2 pi. So notice our bounds: theta 0 to 2 pi, and then for any given value of theta. Any given value of theta, r starts there at 0, and it goes up to there where r is 1. So 0 to 1, and again, polar coordinates. Boom. All right, we avoided a bunch of square roots again. Okay. All right. Couple of observations. Turns out it's almost always best to use this order. dr on the inside, d theta on the outside. Practically always. Not quite always. There are some weirdo examples, but they're pretty weird. They're pretty manufactured. Vast majority of... It's so almost always that I think for the purposes of Math 219, if you just always do dr on the inside, you'll be well served. Right? Right. So that's convenience. You don't have to really think about which way do I want to slice it. Here's another little bit of advice, and I really do hope you always do this. Always write all of this all at once. There is a temptation to write down the differentials first, and then do your slicing, and I'll worry about all this other stuff later. I got so much going on with the shape and the slicing and the bounds, and then you forget. It happens a lot. I've done it myself many times over the many years. To go back and remember, oh yeah, that's right, this is a change of variables, there is a stretching factor, and it's easy just to forget to put that in there. So my solution is always write this down, right, this whole thing here, always write it down all at once. Don't write the dr d theta and promise yourself that you're going to remember the r. That's a gamble. You're playing with fire. Right? And you know it's gonna be there. Why not just write it down all at once? There's zero cost. to writing it down all at once, right? And then you cut down on the, oops, oh my God, I can't believe I forgot that. And just keep in mind, if you do forget that stretching factor, if you forget the R, it's really wrong, right? It makes it look like the student who doesn't include the R in there appears not to understand where polar coordinate integrals come from. It's bad, right? And so you're going to lose points, and I don't want y'all to lose points. So I think this is a really good rule. Always write this down think of it almost as being a single thing, RD theta. You write that down all at once, and you can't forget it. Yeah.
Is there a way to write this in a double integral form as opposed to an iterated integral? Or do you just...
Not really. I mean, so the point is with a double integral, I mean, what defines a double integral is a domain and an integrand, right? And how you choose to slice it is part of the slicing, which is part of making it an iterated integral. So double integrals don't really have coordinate systems. They're kind of, it's a great question. This is really very much an iterated integral thing.
Okay.
Yeah.
So if you were to write, we have to write the double integral too, or else we lose points there. So could you write the integrand of the double integral in terms of R and then write dA?
Oh yeah, that's fine. Yeah, I don't have a position on that. Yeah, that's right. Yep. Totally. Okay, sadly we're out of time. So I guess more examples next time. All right, so there we go. Y'all have a good day. Yeah.